Good morning and happy Wednesday, everybody. So first and foremost, I'm going to start off with a little bit of notes, and here is a little bit about systems of equations. So if we look at the definition of systems of equations as it is defined in our textbook, a system of equations is a set of equations with the same variables. Solving a system of equations means finding one or more solutions that can make each of the equations in the system true. A solution to a system of equations gives a point of intersection of the graphs of the system of equations. There can be 0, 1, or several solutions to a system of equations. So first things first, it's got two equations that have the same variables. So if I have y equals 3x plus 2 and y equals 2x plus 3, I've got y's, I've got x's, we're good to go. That right there is a system of equations. Solving one means finding the one or more solutions. And as we know, when we're dealing with solutions, solutions are the values that make our statement true. So the statement that y equals 2x plus 3 has infinitely many solutions. If we simply go with y equals 2x plus 3, we know that when we plug in 0, the output is 3. We know when we plug in 1, the output is 5. We know when the input is 2 that the output is 7, and we can keep going. And so y equals 2x plus 3 you may recognize as the equation of a line, and a line is a collection of points, and every single point on that line is a solution to that one equation. But when I give you a system of equations, when I'm giving you two equations with the same variables, the solution to that system are only the point or the points that those two equations have in common. So if I give you two equations that have y's and x's, and you put them into slope-intercept form, and you graph them, what point or points do they have in common? Do they intersect at one point where they have one solution? Are they parallel where they're never going to have a single solution ever? Or are they the exact same line where there's infinitely many solutions because they share every single point? These are things that we're going to be exploring. But you need to know the definition for systems of equations. You're going to want to know what I'm talking about when I say a system of equations. And that's why with the many different word problems that we've looked at so far and will continue to look at today, we are creating systems of equations based off of the information provided to us, so that way we can come to a solution. Because some of you may have liked just filling out a table, but I did not like having to create the table for you. Nor do I enjoy having to go, all right, for this equation, I've got this input, that input, this input, that output, this input, that output, and then doing the same thing again. I find it very taxing. I find it very cumbersome. I find it very annoying. So while we will still have a video here in a minute about how to solve a system of equations using a table and using graphs, what we're going to explore today is how to solve one without it. So take a look at the next two videos for a review on solving with a table and solving with a graph, and then we'll dive into the equal values method. Hang tight and click on the next one.